All right. Okay. So we have entered our last part of this introduction to quantum computing, which is we're going to be talking about quantum algorithms. We're going to be going through our first quantum algorithm. Before we get started on this, I'm going to just go ahead and say that the probably the worst way to go through this is by just watching this YouTube video. Uh, this is very much something where it'd be better if we were like, playing around on a board or something like that. Uh, that being said, we do have some notes linked below. There's a Google Drive link in the comments on the YouTube. Probably a better way to learn is to be following through those to actually pick up the details rather than just listening to me ramble aimlessly. But if you're going through the notes and you don't quite understand something, maybe my ramblings will help. We'll see. So before we start talking about quantum algorithms, we should probably start talking about algorithms in general. And what I find helps here is just to think a little bit about just what a computer is. So a computer is something that I provide some input information to. I ask it, what's 2 plus 2? I ask it, show me a picture of a cat. And then on the monitor, I get the information that I actually want. It tells me that 2 plus 2 is equal to 4. It shows me the best picture of a cat that I could possibly want. In the middle is some magic. I'm a physicist. I don't understand anything about computer circuitry, computer hardware. So as far as I'm concerned, this is a magical black box. And that's how most people interact with computers is here's some magical black box. I give it some input. It gives me some output. Okay, so what the computer does is an information processor, which we then use to solve problems. We give it some input, which we can, in general, break down into a binary series of ones and zeros. It gives us an output, which we can also break down into a binary series of ones and zeros. And in the middle, there's a black box, which does some magic, and that magic has to obey certain rules of information processing. So we've already seen that we can encode and process information in a quantum system. We've seen that you can, encode a quantum state, you can code zeros and ones in a quantum state, and you can manipulate them using quantum gates. So what is a quantum computer? Well, a quantum computer is the same thing. Like we're going to give it an input. We're going to give it a classical input that we can understand. It's going to be a string of zeros and ones. We're going to want a classical output that we can understand. It's not useful for it to give us a bunch of spin states that we don't know what to do with. We need a string of zeros and ones at the end of the day that actually gives us an answer to our problem. But in the middle, that black box, that kind of magic shakeup of that data obeys different rules. It is a quantum information processor instead, and it can use things like superposition. It can use things like entanglement. It can use things like the fact that we can measure a quantum state in many different incompatible ways to occasionally process information in a much different and potentially more efficient way. Okay, the black box obeys different rules that can take advantage of these quantum phenomenon. So what kind of problems should we use it for? So we're going to focus on a very useless problem, let's say. It's one that doesn't really, it's not something like a quantum adder or the quantum factoring algorithm where we can, see how it would be useful. But we're going to focus on it because it's something that we can do very quickly on the board to kind of get at some of the ideas of why using these rules can lead to an advantage. If you want to get a full survey of all the different kinds of quantum algorithms there are out there, I recommend quantumalgorithmzoo.org. It's a maintained website run by academics kind of listing all algorithms that people are aware of so far that can benefit from a quantum speedup. Also, a keynote there is that we're not even sure if we found all the ones that have a quantum speedup. In fact, we're pretty sure we haven't. This is a very kind of like the Wild West out there, finding new algorithms that can be improved using quantum processors. You also find people coming up with ones that they think have a quantum advantage that turn out to not have a quantum advantage, but that's a separate story entirely. So the particular kind of problem we're going to be focusing on today is what's called an oracle problem. So what does that mean? So an oracle is basically where we have access to an object that has a lot of information, and we want to find the most efficient way to extract some kind of information from it. So a good example of that is a phone book. A phone book, for those of you who haven't seen one before, they're these giant tomes full of phone numbers for everyone who offered to have their phone number listed in the phone book. So basically, you go into the phone book, you look up someone by their last name, and you get a phone number out. Okay, so basically, the phone book is a database. I give it a name, it gives me a phone number. So let's abstract that kind of concept a bit. The name is the variable. The name is the thing that I know. I know the person's name. I know that I'm searching for Michael Reimer. And f of x is the function that I get out, and that's going to be Mike Reimer's home phone number. So I'm going to give the phone book an input, and it's going to give me an output. Input x, output f of x. Okay, and this is perfectly fine for doing things like finding this specific number. But what about if I want other kinds of information? For example, I don't really care about what Mike Reimer's phone number is. What I care about is how many phone numbers in this phone book have the 519 area code. What I care about is what fraction of the phone numbers end in the number 9 or something like that. So is there an efficient way to get that kind of information out of the oracle? So we're really looking at a collective property of the outputs, not of one specific outputs. I care about all of the possible outputs, and I want to find some kind of collective property of them. And this is kind of the idea behind the Deutsch-Josza problem. So it was a problem proposed by David Deutsch and Richard Josza sometime in the early 90s. And it kind of looks like this. There exists a binary function f of x. So that's going to be our output there. It has two possible inputs. You can either say x equals 0 or x equals 1. And two possible outputs. F of x is equal to 0 or f of x is equal to 1. When you put it like math, it doesn't make any sense. So, let's put it into a physical context. Basically, what we have is a box. And that box has two buttons on it, 0 and 1. I'm allowed to press the 0 button or the 1 button. Every time I press a button, a light bulb goes on. Either this light bulb or this light bulb. In fact, I have the box right here. It's got two buttons. Every time I press a button, a light bulb goes on. But it's unclear until I press the button which button turns on which light bulb. In fact, I could have situations where no matter which button I press, so press the left button there, press the right button, the same light comes on with both button presses. There's something going on in the middle that's kind of hiding the wiring from me. And that's the function that I want to know. I want to know, given which button I press, which light bulb comes on. So if you think about this for a bit, you can probably convince yourself pretty easily that there's 4 possible situations. Given that I promise you that each button press corresponds to exactly 1 light bulb going off, you could have the situation where the button that you presses corresponds exactly to the light bulb that comes on. So I press button 0, light 0 comes on. I press button 1, light 1 comes on. I could have the case where it's the opposite. I press button 0, light 1 comes on. I press button 1, light 0 comes on. I could have the case where no matter which button I press, light 0 comes on. And I could have the situation where no matter which button I press, light 1 comes on. There's no other possible functions that can arise here. Okay, so these are all 4 possibilities, and we're going to label those f1 of x, f2 of x, f3 of x, and f4 of x, corresponding to these truth tables here. Now, if we kind of look at what's going on overall here, we have 2 functions that are constant. By constant, I mean no matter which button I press, I always get the same light bulb coming on. Okay? Doesn't matter which button I press, I always get the same light bulb. And I have 2 functions that are balanced. Whenever I press one button, one light bulb comes on. Whenever I press the other button, the other light bulb comes on. There's kind of a balance in which button I press and which light bulb comes on. They're always it's one or the other, and they both have an equal number of buttons that turn their respective light bulb on. So to determine what function we have, if I ask you the question, do I have f1 of x, f2 of x, f3 of x, or f4 of x, you need to press both buttons. If I give you this box and I don't tell you what function there is, you press button number 0 and light bulb number 1 comes on, that's all good. So button number 0, light bulb number 1, that means I have either f3 or f4. But I don't have enough information to tell you if it is F3 or F4 until I also press the other button. And in this case, it turns out to be F4. So effectively what this means is that I need 2 queries to solve the problem. Okay? But what about if I'm not asking that? What about if I'm instead not asking you to find exactly which function it is, but I'm asking you to find if the function is constant or balanced? Okay? So let's do the same thing again. I'm going to put another random function into my box. I got a bunch of switches on the back to make random functions. So I got a random function in my box, and now I'm asking you, is it constant or balanced? You press one button. So button number 0, light number 0 comes on. So that means you have either F1 or F2. Is the function constant or balanced? Well, F1 is constant, F2 is balanced. I have no way of knowing which one of the two it is until I press this Second button, in this case, find that it's balanced. So I need two queries to find out whether the function is constant or balanced. There's no better way to do it. Okay, so for this problem, classically speaking, I need to press both buttons to find out if the function is constant or balanced, which is the same amount of presses that I need to figure out exactly which function I have. So the classical Deutsch-Josza oracle, like the oracle really is the box. So basically what happened is I asked the oracle to program the function into this black box. But that was pretty arbitrary. It could have, asked for any other possible way to encode that. And if I did that using any other classical method, I guarantee you that you would not be able to do better than the two presses situation. Okay, but let's say we're able to ask for the oracle as a quantum gate instead. Okay, so we still are going to we're going to have a function, and that function f of x obeys the same rules, and we still want to find out the same thing. We want to find out whether or not that function is constant or balanced. But I'm asking for that oracle as a 2-qubit gate. And the action of that gate is as follows. It takes 2 qubits, one labeled x, one labeled y. So these are both 2 qubits, so x can equal 0 or 1, and y can equal 0 or 1 as well. What the unitary does is it leaves x alone, and the y qubit, the second qubit, is exclusive ORed with the value of the function at x. Okay, so exclusive OR, sorry, addition x, yeah, exclusive OR. It's addition modulo 2 or bitwise addition. So if y is 0 and f of x is 0, 0 plus 0 equals 0. If y is 1 and f of x is 0, 1 plus 0 is equal to 1. If y is 1 and f of x is 1, then 1 plus 1, we roll over and take that to 0 because it's an exclusive or we get rid of the remainder if we're thinking about addition modulo 2. Doesn't matter too much there. So yeah, we have a 2-qubit unitary which has the function f of x programmed into it in this exact way. Let's break it, I know the first time I saw this, I was just like, what is happening here? So let's break it down with an example case. Basically what it's saying is that if f of x is equal to 1, so if the value of that button press is light bulb 1, flip the bit y, flip it from 0 to 1 or 1 to 0. If the value of f of x is 0, if it would cause light bulb 0 to come on, don't do anything. Okay, we're going to call this guy here the x qubit, the control qubit, and we're going to call the y qubit, the bottom one, the target qubit, because the state of the x qubit controls whether or not the state of the x qubit combined with the function value at the value x controls the state of the y qubit on the output. Okay, so let's go through an example. Let's say we have the function f2 of x. So this is the one where if you press button 0, light bulb 1 comes on. If you press button 1, light bulb 0 comes on. So kind of you get the opposite of x as your output. So if we apply our unitary on the state 0 and then any arbitrary y value, here says y could be equal to 0 or 1. Well, okay, the value is 0, y exclusive OR with f of 0. F of 0, so if I press button 0, I get light bulb 1. So f of 0 is equal to 1. So my output is 0 and y exclusive OR with value 1, which is equivalently saying flip the bit y. So 0 and not y is my output. If y is equal to 0, then I get 0, 1. If y is equal to 1, I get 0, 0. Okay, UF, now let's go with this situation here. Instead, I have a unitary F acting on the state 1 and y. So my control qubit is in the state 1. My target qubit is in an arbitrary state. So now what I get is 1, y exclusive OR with f of 1. So if I press button 1, light bulb 0 comes off. So f of 1 is equal to 0. So basically, anything exclusive OR 0 doesn't do anything. It doesn't flip y this time, so I get 1 and the same state. If I sent in y equals 0 originally, I get the state 1, 0 on the output. So in each of these cases, know that the control doesn't change, and the control is always the same as it started with, and the target either flips or doesn't flip. So what if we send in the computational basis states here? So if we send in the state 0, 0, we get the output being 0, f of 0. If we send in 1, 0, we get 1, f of 1. Because, yeah, if we look back here, so if y is equal to 0, then we just get the value of the function at the value x going in. So, okay, if we send in the computational basis states, then the output of the function is encoded in the state of the target qubit. By measuring the target qubit in the z basis, we can figure out what f of 0 is, what f of 1 is, and with 2 queries figure out if the function is constant or balanced, and indeed figure out exactly what the function is. So the classical method works just as well. But what if the control is in a superposition state, okay? What if we take this control qubit here, x, and we encode it in, say, the plus state? Okay, so we're going to use our favorite tool, linearity, to expand that into 2 terms. So this plus state, remember, is 0 plus 1 over square root 2. So if we expand that out, we get 0, we get a term that's 0, 0. UF on 0, 0 is 0 f of 0. So that comes out here. And we get a term that's 1, 0. That comes out here. And what we end up with is 0 f of 0 plus 1 f of 1 over square root 2 for normalization. So this is neat because we see that in the output state, there is something about f of 0 and something about f of 1. Both f of 0 and f of 1 are in the output state. But if I measure the qubit, then I'm going to either get information about f of 0 or information about f of 1 randomly. I don't get information about both at the same time. But we can already see that something is getting a little nifty here because both of these states end up in there. We just need to be a little bit more clever about how we get them there. So like I said, this is where, if you haven't already lost the plot by just listening to me ramble, this is where it's going to get really messy. So I highly recommend going through the notes first and then kind of coming back to this once you're kind of primed to know where this is going. So let's send in this state. So we're going to put what if the control and the target are both in a superposition state? Okay, so for example, send in the state plus for the control. So the control qubit is in the positive superposition. The target qubit is in the negative superposition state. Okay, so that gives us our unitary, our 2-qubit unitary acting on the state plus minus. We once again expand that out using linearity. So plus is 0 plus 1, minus is 0 minus 1. And now we're going to expand that out, and we see that we have 0, 0, minus 0, 1, plus 1, 0, minus 1, 1, with our unitary still having yet to be applied. Next, we're going to use the rules of our oracle to further expand this. So we apply u of f on 0, 0. We saw before exactly what that does. U of f on 0, 1, we know exactly what that does. U of f on 1, 0, we know exactly what that does. And u of f on 1, 1, we know exactly what that does. You end up with kind of a mess that looks like this. Okay? So it looks a little messy, but everything is what we expect. 0, 0 goes to 0. 0, the exclusive OR with f of 0. 0, 1 goes to 0. 1, exclusive OR f of 0. But we do have to make sure to keep track of these plus and minus signs here. Those are going to be very important. Okay, so we've used our oracle rules. This is the exact same equation we saw before, just copied up at the top. Now, there are ways to find special things out of this, and those are in the notes, but let's just look at some special cases to get an idea of what happens at the end of the day. So let's look at the special case where we had the function f of 1. So that's no matter what button I push, the 0 is my output. So okay, f of x is always equal to 0. So if f of x is always equal to 0, it basically never flips anything. So 0, 0 stays 0, 0, 0, 1 stays 0, 0. Sorry, 0, 1 stays 0, 1, 1, 0 stays 1, 0, 1, 1 stays 1, 1. And I can just simply recollapse that back to the original state. So effectively, the unitary did nothing. And I get my original state out plus minus. If I instead have f of 2, so that's where f of 0 equals 0, f of 1 equals 1, then what that means is that it's going to flip in all the cases where we have this f of 1 term here. Okay, so the 1, 0 is going to flip to 1, 1. The 1, 1 is going to flip to 1, 0. Yeah, and which we can see here, the 1, 0 flip to 1, 1, the 1, 1 flip to 1, 0. Now then, if we look, remember, those minus signs, those didn't change. So now instead of the 1, 1 having the minus sign, the 1, 0 has a minus sign. If, and this is probably easiest to check in reverse, I can recollapse this state back into the state minus minus. So the plus here, the original positive superposition in the control qubit, has become a minus superposition, a negative superposition, 0, minus 1. We can do this for all the different ones. We're not going to go through the gory details there. Once again, this is really something I recommend doing pen and paper at home. And we get something like this. We get plus minus for f of 1, minus minus for f of 2, minus minus with a pi phase for f of 3, plus minus with a pi phase for f of 4. This is what we call a global phase out here. It matters if we're querying things in superposition, but does not matter if this is our whole system here. And this is what we're looking at. Like we don't see the effect of a global phase on measurement. Okay, cool. So we've done this. And now for the two constant functions, f of 1 and f of 4, the two where it doesn't matter which x I send in, I always get the same output out. The control qubit is in the plus state. So for all four of these, the target qubit's in the minus state. Nothing ever changed about the target qubit. But if the function is constant, the control qubit's in the plus state. If the function is balanced, if when I press one button, one light comes on, another button, the other light comes on, doesn't matter which order that goes, then the control qubit is in the minus superposition state. So if I measure the control qubit in the x basis, if I ask the question, are you plus or are you minus, I can tell if the function is constant or balanced in only one query, which is something that we just showed earlier is impossible to do classically. Okay, so by using this quantum algorithm, we can do something more efficiently than we could possibly do classically. All right, so the circuit looks something like this in the circuit model. We're going to initialize both states to 0. We're going to prepare the plus and minus superposition states. So H is going to convert this 0 to a plus. An X followed by a Hadamard is going to prepare this state into the minus. We're going to apply our 2-qubit Deutsch-Josza unitary, and then we're going to measure the control qubit in the plus-minus basis using the Hadamard followed by a Z measurement. So if you want to program around this, so this is what the circuit looks like in the IBM quantum experience. So what I've dashed out here is the Deutsch-Josza oracle for f of x equals 1. You have to play around with that to figure out exactly how to implement that oracle. But we see here that we create our minus state, we create our plus state, and then we measure in the x basis. And on the simulator, what we see here, don't worry too much about this, but on the simulator, we see that we always measure the output 0. And that tells us that's the output 0. So always measure this state, this final state in the state 0. That tells us that our function is constant. If we always measured 1, that would tell us that our function was balanced. We can also try to run this on the real hardware. So if you wait long enough, you can send it to an IBM machine, and we see now about 80% of the time it tells us our function is constant. About 20% of the time it tells us it's balanced. This is because real hardware, especially right now, is just not as reliable. And when we start talking about implementations later on, you'll kind of understand why. But it's something that people are obviously actively working towards. This is not a very complicated algorithm, but on the publicly available quantum processing units, it's enough to mess things up. Okay, so preparing the target in a so why did this work? Let's kind of dive into the guts of this, because once again, this is a very useless problem. But what can we learn about how quantum algorithms work by studying this problem? So preparing the target in a superposition state wasn't enough. We saw the first time we tried that, let's put the target in superposition and maybe we'll be able to get the answer out. It was also important that we measured in a superposition basis, that we measured in the X basis. So this is really the first rule of Quantum Computing Club. And if you've seen some tweets or something about quantum computing, you might think, oh, we're just querying all possible superpositions at once by expanding our state into some superposition of all possible states that allows us to query every single possibility in multiple universes all at the same time. And no, that's not true. It's not just about querying all possible superpositions. In a sense, that's part of it, but that's only true if you also take advantage of measurement. Superposition is only useful if you're also clever about which measurement context you measure in at the end of the day. Okay, so this part is just as important as this part. Why did it work? So note that the target qubit wasn't actually measured, the one that had the action applied to it. So the unitary either flipped or didn't flip the Y qubit. But ultimately, the Y qubit wasn't the one that we measured. We measured this first qubit, the control qubit, the one that we've been calling X. So in the notes, we kind of derive this equation to kind of talk about why that happened, but this is something called phase kickback. Kind of the phase that control qubit picked up was kicked back to the target, sorry, the phase that the target qubit picked up was kicked back to the control qubit. And this kind of idea of phase kickback is important to a lot of quantum algorithms. The fact that something that happens here can kind of kick itself back to the original qubit, to the target, to the control qubit. And this is a key to many quantum algorithms. Also, why did this work? So now with one query, we can tell, is the function constant or balanced? But we still have no idea what the function is. I can tell you, if I get the output 1, that the function was f of 2, it was f2 of x or f3 of x. It was balanced. If I get the output 0, I can tell you it was f1 of x or f4 of x. It was constant. But in order to figure out was it f1 or f4, I need to make another measurement. So I still need 2 queries to know which f of x I have. Okay? So using the quantum algorithm allowed me to extract a property that I wasn't able to extract using the classical algorithm. But it's not all powerful where I can know exactly which function I have in only one query, okay? So the second rule of quantum computing is that quantum computers can be used to speed up certain tasks, but they don't speed up everything, okay? If I want to know which function I have, I still need to make 2 queries. All right. Just going to flash this real quick. Not going to get into the details here. There are more details in the notes linked below, but this does scale up to many qubits. I can think of another form of this problem where I'm asking if the function is constant or balanced, and effectively, as I increase the number of bits of the function, if I increase the number of possible output combinations, the possible input combinations, the difficulty of this scales exponentially if I want to be 100% positive. However, the quantum algorithms can still do it in exactly one query. This is an exponential quantum speedup. There are a lot of disclaimers that should be attached to that. Depends on if you're willing to accept any error, because this problem is not hard if you're willing to accept a little bit of error. But if I want to be perfect, if I want to define my problem in a very specific way, then this is an example where I get an exponential quantum speedup. Like I said, details are a bit complicated. You can check out the notes for those full details. All right. So why do quantum computers make we can get that kind of exponential speed up? Why can we get that? So remember what we saw earlier is that classical bits can be 0, 1, or anything in between, but 0, 1, anything in between, but that's about it. It's just like the probability of it being 0, the probability of it being 1 is what gives me the full information about what that bit is. Quantum states, however, can exist at any point along the sphere. Effectively, what this means is that I only need one measurement to know the exact state of the classical bit. I need to know the probability of it being 0, which tells me the probability of it being 1 by normalization. But in order to figure out this quantum state, I need more measurements. I need to know more things. I need to know both this angle, this phase. There's also the idea of mixed states. I need to know if it's on the surface of the sphere or inside the sphere. Effectively, I need to know one number to know what this state is. I need to know 3 numbers to know this state here. Now let's expand this to larger and larger numbers of bits in qubits. So this, the complexity of this is going to scale as 2 to the power n. As I have n bits of information, I can encode 2 to the n numbers in there. This is kind of, the rice on a chessboard problem, effectively. 2 to the n real numbers will describe how this state grows. In the quantum space, though, because I need 4 measurements for each bit, and I need to think about how these bits are all connected together as well, I need 4 to the n real numbers to describe my system of quantum bits, which is 2 to the n times 2 to the power n. So I get an extra 2 to the power n down here. That leads to an exponential separation in the complexity. The quantum entangled states are exponentially more complex than the string of classical bits. Okay? So this exponential separation can sometimes be harnessed to process things in different ways, but you need entanglement and you need to be able to measure in superposition bases to do this. It's not just enough to spread it out along all these quantum bits if you don't have entanglement and you don't have the ability and cleverness to measure in different superposition bases. Okay, so quantum computers do not provide an exponential enhancement for every problem. For factoring, for example, that's a particularly famous one that happens to be exponential. Search is another very famous one. That's only a quadratic speedup, a square root speedup. For many other algorithms, nothing. There's no reason why a quantum computer would ever be used for document processing or for adding numbers together. The adding algorithm is already optimal. There's no reason to change that by using a quantum computer. For many, many others, like I said, it's the Wild West. We don't know exactly. Like there's even classical computer science, there's a lot of unknowns in terms of whether or not we found the optimal algorithm for certain things. So for uh, quantum computing, it's an even kind of more unknown region where we're trying to figure out what can quantum computers be used for to speed up. But as I said, check out the quantum algorithm zoo to see what we already know they can be used for. Now, then to build them in the lab, we've been kind of focusing on them from an abstract perspective here. We haven't been focused on, you know, specific implementations, but you can build them out of many things. You can build them out of the energy states of a valence electron trapped in a charged ion in a linear Paul trap, or out of the energy state of a cluster of neutral atoms in some kind of condensate. You can build them out of photons in the polarization state of the photon and where a photon is, where its position is. In the spin state, either if we're talking about like the spins in a molecule in some kind of NMR experiment, we're talking about the spin of a quantum dot or something like that. We could be looking at superconducting circuits where we design our own artificial atoms in a clean room and encode based on some flux properties or something like that. So here are kind of like just like very quickly, and also in many ways very unfairly, a kind of list of folks at the Institute for Quantum Computing and what kind of systems they study. So we have people at the University of Waterloo studying each of these systems in many different ways. Which you might be thinking, okay, they're professors. They just study what they learned about in grad school, and they'll keep studying that until the day they die. But we also see many companies also studying each of these different implementations. So, for example, Google and IBM are pretty famously working on the superconducting circuit approach. Intel's working on the spin approach. We have a lot of companies, including Xanadu in Toronto, studying the photonic approach. Honeywell and IonQ studying the atomic ion approach. So what's the future quantum computer going to be built out? Could be any one of these, could be another thing entirely. But there's a lot of work going on, both in KW and around the world, on many different ways to actually build these things to make them work. And with that, I'd like to thank you very much for tuning into these once again. And yeah, hope you have a wonderful day. Please, if there are any questions, don't hesitate to send me an email. I'm more than happy to hop on a chat. All right. Thank you so much.